Um, okay, the other best paper, the other winner of the MACD Award for Best Student Paper is Faster Minimum Cut of a Simple Graph by Jason Lee.
Okay. Well, I'm from Carnegie Mellon University. I forgot to add that in. Okay. So in this talk, we'll consider the K-cut problem. So given a weighted undirected graph, delete the min-weight set of edges that splits the graph into at least k components. And in this talk, the regime we'll consider is the exact algorithm, and think of k as like a large constant. So for example, if k is 5, we can imagine splitting the graph into 5 pieces, and the edges we pay are the edges whose endpoints belong in different pieces. So prior work on this problem is known to be polynomial time solvable when k is a constant. And until last year, all of the algorithms, both randomized and deterministic, have run in time roughly n to the 2k time. The two most notable results are the Karger-Stein algorithm based on randomized contractions and Thorup's algorithm based on tree packings. And last year, or this year, myself and a few collaborators have improved the bound from n to the 2k to slightly less. And this one used techniques from both the tree packing and the randomized construction. And we also have a different result where we only consider graphs that are of integer weights. And here we can also beat the n to 2k running time. And this work, we improved we improved the running time even further from these two results to roughly n to the k time. And here, O sub k is hiding dependence on k, where we treat as a large constant. But the downside is this only works on simple graphs, and these are unweighted graphs with no multi-edges. On the lower bound side, it's known that k-cut is roughly as hard as k-cleek for roughly the same parameter k. And based on a popular conjecture on the hardness of k-cleek cannot be solved in n to the omega over 3 times k time for algebraic problems using fast matrix multiplication, or roughly n to the k time for combinatorial algorithms. And it turns out that the algorithm that we consider in this work turns out to be combinatorial. So this gives us a tight running time for k-cut, assuming the combinatorial k-cleek conjecture. So I'll begin with a brief outline of the algorithm. It'll consist of multiple steps. So the first step is, given an input graph G, we want to sparsify this graph to reduce the number of vertices. So we use a sparsification routine due to Kobayashi and Thorup that says that given a graph G, we can sparsify the graph to preserve the min cut structure, in this case the min k cut structure, and the number of vertices is much lower. So here, lambda k is the value of the min k cut of the graph, and we adapt their sparsification to show that we can reduce the number of vertices to n over lambda k. And we want to preserve the min k cut of the graph, so we can solve the graph on the sparsified instance. We need to assume that the k cut is non-trivial. We'll get to this later on, but this is a small technical thing that we can handle. The next step is we run a tree packing routine. So it's known that we can, given a graph, we can we can compute a collection of roughly n to the k trees, where now n is the smaller n bar, such that there exists, given an optimal k cut, there exists one tree in the collection that intersects the cut roughly exactly k minus 1 times, and this is optimal. So you can see this picture right here. And finally, this third step is now we can reduce this problem into a problem on trees. So by paying this n to the k overhead, where we run this on each tree, we can solve a problem that's completely on trees. So given a tree, we want to cut some k minus 1 edge of this tree, and this will induce some k cut. We want to find the k minus 1 edge to remove to get the best k cut. And this is our main technical part of our paper. We use the techniques of color coding from fixed square retractability, and heavy light decomposition on trees to produce a result, to produce an algorithm that runs in roughly lambda k to the k time. Okay. And if we sum all the running times, we get, so n bar, the actual n that we consider is actually n, the original n over lambda k. So we pay time n bar to the k times lambda to the k, roughly, which turns out to be roughly n to the k. So that's our structure. And note that the techniques we use come from various different algorithmic fields. For example, graph sparsification from graph algorithms, tree packing from linear programming, and color coding from fixed square retractability. Okay. So we'll go over the three main parts in order. So we'll begin with sparsification, and we'll talk about tree packing, and finally we'll briefly outline the color coding step in the tree problem. Okay, so let's begin with vertex sparsification. So in 2015, Kobayashi and Thorup showed that for any simple graph G, we can contract some edges of this graph into, now it's maybe no longer simple, maybe multi-graph, such that no non-trivial min cut has any edges contracted. So by non-trivial, I mean a min cut that has at least two vertices on each side. So no such min cut will have any edges contracted. And we want a vertex reduction. We want the number of vertices to be reduced by a factor roughly lambda, where lambda is the min cut value. So you can imagine, given a graph where you can imagine like these are the densely clustered parts of the graph where there are no min cuts that cut through it. We can safely contract those dense clusters into single vertices. In this case, the min cut is 3, so and you can see that the min cuts are not destroyed. Okay. A second example, an instructor example to consider is whether the input graph is a complete clique. Well, in a clique has no non-trivial min cuts because the only min cuts of a clique are the singleton vertices, and these are trivial. So for a clique, you can just contract the entire thing to a single vertex. That should be fine. Okay, so Kobayashi and Thorup use this sub-sparsification routine to show that there's a deterministic min cut algorithm that first sparsifies the graph into, now here they use an edge reduction here, and then they run an algorithm on the sparsified graph in time lambda times the new number of edges to get a near linear time overall. So that's how they use their sparsification routine. So and finally, trivial min cuts are easy for them because these are just degree cuts. So in our work, we adopt the algorithm as follows. We adopted instead of a min cut problem, we now consider a min k cut problem. We need one regularity condition that we're able to handle with some work, but we'll not see in this talk. We need the condition that the min k cut is not too much larger than the min cut. So some function of k, they're close apart by some function of k. So again, non-trivial for min k cut just means that still each component now has at least two vertices. And now on the sparsified graph, we're going to run an algorithm in time, not lambda times number of edges now, but lambda k to the k times number of vertices to the k. And finally, I want to claim that the trivial min cuts are still easy. Why is that? That's because a trivial min cut has at least one component with a singleton vertex. So we can just guess, loop over all the vertices, guess which one's a singleton, and just recursively call k minus 1 cut. So that's easy. Okay. So the second step of the algorithm is we want to solve the problem on a sparsified graph. So we have a vertex reduction where now this new n that we'll call n from now on is the old n over lambda. So this running time is sufficient. So the second step in our routine is the tree packing. And so The most notable tree packing result for the K-cut problem is due to Thorup. Thorup showed that given any weighted graph, you can compute a collection of trees, a polynomial number of trees, such that for any minimum K-cut, there exists some tree that intersects the tree in at most 2k minus 2 edges. So by that, I mean like this. So the blue tree intersects the optimum K-cut on the red edges, and there are at most 2k minus 2 of these. So this is what Thorup showed. With my collaborators, we showed that we can modify the statement a little to produce more spanning trees, now n to the k spanning trees, not just poly n. But we have a benefit in that there's some tree in this larger collection that intersects the min k cut only k minus 1 times, and k minus 1 is optimal. So by applying this tree packing and paying this n to the k factor to try it on each tree, we can reduce the problem to, given what I'm going to call a tight tree, delete the best k minus 1 edges to form the smallest k cut possible. So here's the example. So given a tree, and some extra edges of the graph, we're going to find some k minus 1 edges to delete to induce some k cut out, of the graph. And these are the edges that we need to pay for are just the edges whose endpoints are different components. And again, our time needs to be, so now that we've paid this n to the k factor, our time needs to be roughly lambda to the k times a lower order term. And note that lambda sub k to the k is fixed parameter tractable in lambda k and k. But here, the particular dependency matters. We really need lambda k to the k. Not even 2k in exponent would be good enough for us. So it makes sense that we will be resorting to FPT techniques to solve this problem. Okay, so that's our problem to solve. In this talk, we'll consider the case when the tree is a spider. So that basically means that the tree has a root, and aside from this root, all the other vertices belong to branches hanging off from this root. The paths hanging off from this root. We'll make the additional assumption that the optimal k-cut cuts at most one edge per branch. So it picks some k minus 1 branches and cuts one edge from each branch. So in this case, it cuts the first, third, and fifth branch. Again, this is the induced k-cut based by cutting these branches, and we pay for these edges. So there's two issues to overcome in this approach. The first one is, which branches do we choose? So naively, there's the number of branches choose k minus 1 choices for which branches we pick. That's too much. And the second difficulty is that suppose we can even identify the branches. How do we find the best edges to cut? Note that we cannot just find the best cut in each branch and sum over all the boundaries, because we might double count one edge, where we've counted this edge cut from both sides. But note that if there were no such edges between two different branches, so for example, if every edge, the two endpoints belong to the same branch, then we can do this. What we can do is we can, for each branch, take the best cut in that branch and sum overall, and take the best k minus 1 overall out of all the branches. This will not double count, this will give us the right answer. So it makes sense, so that's one extreme case. Let's consider the other extreme case, where there are a lot of edges between branches in the optimal solution. In this case, we'll apply a color coding scheme to help us identify the particular branches. Okay, we'll color code some spanning tree on these branches. So by that I mean the follows. So suppose again the opt cuts the first, third, and fifth branch. We want a spanning tree connecting the first, third, and fifth branch. So here, a spanning tree is only two edges, the purple edges. And we want to color the edges either green or red. Let's say in a successful color coding, we color we color the entire spanning tree green, So we fix the spanning tree beforehand, and we declare success if we color each of those edges green. Moreover, for each of opt's branches, so the branch hanging from the root, we want to color the remaining boundary edges red. So what does that mean? That means, so let's take the first branch, for example. All the red edges are edges on the boundary of this branch. So the edges connecting this branch with something else. We want to color each of those red. So for the middle branch, those are the additional edges that we need to color red. And that's for the third branch. Okay. So how many red edges can we color? Without loss of generality, we can assume that every edge cuts at most, if we cut every edge of the graph, of the tree, we cut at most lambda k edges. That's because if we could cut, if there was an edge that cut more than lambda k edges, then opt can never cut this edge, because that will give you at least more than lambda k edges already. So we can contract those edges. So there's at most lambda k edges, lambda k red edges per branch, and that's k times lambda k total. The red edges that we have to color. So now if you imagine contracting every branch, you get a connected component of green edges that is exactly the branches that opt picks. So here we can completely figure out which branches opt took. Yeah, success probability is this following expression, and by setting a judicious value of p, we can get a running time. We can get a success probability of 1 over lambda k to the k times fpt and k. So the high-level idea from this slide is we're highlighting some small structure of the graph. Here is some fixed spanning tree. And we want to color the spanning tree so that we can figure out the spanning tree from the rest of the graph. Okay. So I'll skip double counting for this talk. Let's consider the problem of general trees. So in general trees, to reduce the case when the tree is a spider, we use heavy light decomposition. And we break the tree into branches via heavy light decomposition. And we color each branch either red or blue with the following properties. We want every branch containing an edge cut by opt to be blue. And for each such branch, we want all its ancestor branches to be red. And by the heavy light decomposition guarantee, there's at most log n ancestor branches per blue branch. If we color every branch blue with probably 1 over log n, again, a specific value of p, then we get the following success probability. And this log n to the k term turns out to be fpt and k. So that might be surprising, but that's not an issue for us. And then now, once we contract the red branches, each of the blue branches now is connected to the root, so we're back in a spider case. Again, this assumes that the opt edges are incomparable. So this is one crucial assumption, because it might be the case that one edge of opt is an ancestor of another edge of opt. In that case, this can never happen. So to handle incomparable edges, we need to use some dynamic programming to reduce the case of all of the edges are incomparable. And this is also done in previous work. Okay. So for future directions, one natural question to ask is, can we extend this? Can we produce faster main k algorithms on more general classes of graphs? So what if graph is a general weighted graph? And in ongoing work, turns out this is possible. So with my collaborators, we showed that the min k can actually be done in time n to the k times some subpolynomial factor. So this is this unpublished work. And surprisingly, actually, the Karger-Stein algorithm will actually do that. So if you run the Karger-Stein algorithm, we show that a fixed main k cut will be output with probably roughly 1 over this value right here. And this improves the Karger-Stein bound of n to 2k. And I'll give a TCS plus talk on this about a week from now. So this is exciting. One last question is, what about, can we make this deterministic? Since the Carter sign algorithm is randomized. And that's still not known. I guess that's it.
Okay, any questions? What is the best known deterministic algorithm?
So the n to the 1.99 time, I think can be made deterministic. We just have not put an effort into doing it. But that's not like formally stated anywhere in the literature. But it would be cool to like bring this down to n to the k as well.
Other questions? Okay, then let's thank Jason again.